Good day everyone. I am Dr. Jisha Mishra. Today we are going to delve into a important aspect of electronics, the common base configuration of transistor. Let's begin by understanding what transmitters are. Transmitters are tiny semiconductor device that can amplify or switch electronic signals. And in fact, due to the integrated circuit, the modern day computers and other electronic gadgets which we are using is possible, as it is well known that the bipolar junction transistor BJT is their terminal semiconductor device. The advantage of the 3-terminal solid state device, it is smaller and lightweighted, it has no heat requirement or heater loss, it has a rugged construction, it has more efficient since less power was absorbed by the device itself and lower operating voltages where possible. It has both current and voltage gain. Some key features of common ammeter configuration: input impedance is medium, output impedance is high, phase angle is 180 degree, voltage gain is medium, current gain is medium, power gain is very high. Now we are talking about common base configuration. In common base configuration, as shown in the figure 1, ammeter is the input terminal and the collector is the output terminal, and the base terminal is connected as a common terminal for both input and output. Now you can clear from the figure 1. That means the ammeter terminals and common base terminals are known as the input terminals, whereas the collector terminal and common base terminal are known as the output terminal, which is shown in the figure number 2. The supply voltage between base and ammeter is denoted by VBE, while the supply voltage between collector and the base is denoted by VCB. The common base CB configuration of NPN and PNP transistors is shown in the figure 3A and 3B respectively. The working principle of PNP transistor with CB configuration is same as the NPN transistor with CB configuration. The only difference is NPN transistor free electrons conduct most of the current, whereas in PNP transistor the whole most of the current. Now you can say figure 3A is a NPN transistor common base configuration and the figure 3B is a PNP transistor common base configuration. As the base emitter junction JE is always forward biased and the collector base junction JC is always reverse biased. Therefore, in the common base configuration, the base emitter junction JE is forward biased and the collector base junction JC is reverse biased. Current flow in common base configuration: due to the forward bias voltage VBE, the free electrons majority carrier in the ammeter region experience a repulsive force from the negative terminal of the battery. Similarly, holes majority carriers in the base region experience a repulsive force from positive terminal of the battery. As a result, the free electrons start flowing from ammeter to base. Similarly, holes start flowing from base to ammeter. Thus, free electrons which are flowing from ammeter to base and hole which are flowing from base to ammeter conducts electric current. The actual current is carried by free electrons which are flowing from ammeter to base. However, we flow the conventional current direction which is from base to ammeter. Thus, electric current is produced at the base and the ammeter region. Current flow in common base configuration, as figure 4 show the free electrons flowed from ammeter to collector. From the figure 4, it is seen that the width of the base region is very thin. Therefore, only a small percentage of free electrons from ammeter region will combine with the hole in the base region, and the remaining large number of free electrons cross the base region and enters into the collector region. A large number of free electrons which entered into the collector region will experience an attractive force from the positive terminal of the battery. Therefore, the free electrons in the collector region will flow towards the positive terminal of the battery. Thus, electric current is produced in the collector region. Current flow in common base configuration. The electric current produced at the collector region is primarily due to the free electrons from the ammeter region. Similarly, the electric current produced at the base region is also primarily due to the free electrons from ammeter region. Therefore, the ammeter current is greater than the base current and the collector current. The ammeter current is the sum of base current and the collector current. Now, I E equal to I B plus I E. So, that we can say ammeter current is equivalent the addition of the current collector current and base current. The base ammeter junction presents J E at input side act as a forward bias diode. So, the common base configuration has a low input impedance, low opposition to incoming current. On the other hand, the collector base junction presents J C at the output side, act somewhat like a reverse bias diode. So, the common base configuration has output impedance. The working principle of PNP transistor with CB configuration is same as the NPN transistor with CB configuration. The only difference is the NPN transistor free electrons conduct most of the current, whereas in PNP transistor the whole conduct most of the current. The fully describe the behavior of a transistor with CB configuration, we need two sets of characteristics. First is input characteristic, the second one is output characteristics. Now we are talking about input characteristics. The input characteristics describe the relationship between input current I E and the input voltage V B E. First, draw a vertical line and horizontal line. The vertical line represents y axis and the other horizontal line represents the x axis. The input current or ammeter current I E is taken along the y axis vertical line and the input voltage V B E is taken along the x axis horizontal line. Input characteristic, the output voltage V C B is increased from 0 volt to certain voltage level 8 volt and kept constant at 8 volt while increasing the output voltage VCB. The input voltage VBE is kept constant at 0 volts. After we kept the output voltage VCB constant at 8 volts, the input voltage VBE is increased from 0 volt to different voltage levels. For each voltage level of the input voltage VBE, the input current IE is recorded. Input characteristic. The figure 5 show the input characteristics of BJT when the output voltage VCB is increased from 0 volt to a certain voltage level 8 volt. The ammeter current flow will be increased, which in turn reduce the depletion region width at ammeter junction. As a result, the cut in voltage will be reduced. Therefore, the curve shifted towards the left side for higher value of output voltage VCB. Input characteristic. The cut in the voltage of silicon transistor is 0.7 volts and germanium transistor is 0.3 volts. In our case, it is silicon transistor. So, from the above graph, we can see that after 0.7 volt, a small increase in input voltage VBE will rapidly increase the input current IE. Output characteristics. Now, we are talking about the output characteristics of CB configuration. The output characteristics describe vertical line represents y axis and the horizontal line represents x axis. The output current or collector current presents IC is taken along the y axis vertical line and the output voltage VCB is taken along the x axis horizontal line. Relationship between output current presents IC and the output voltage presents VCB. To determine the output characteristics in the input current or ammeter currents presents IE is kept constant at 0 milliampere and the output voltage VCB is increased from 0 volt to different voltage levels. For each voltage level of the output voltage VCB, the output current ICE is recorded. Output characteristics. When the ammeter current or input current presents IE is equal to 0 milliampere, the transistor operates in the cut-off region. The input current IE is increased from 0 milliampere to 1 milliampere by adjusting the input voltage VBE and the input current IE is kept constant at 1 milliampere while increasing the input current IE, the output voltage VCB is kept constant. After we kept the input current IE constant at 1 milliampere, the output voltage presents VCB is increased from 0 volt to different voltage levels. For each voltage level of the output voltage VCB, the output current presents IC is recorded. Figure 6 shows, now we are talking about the figure 6 of output characteristics. Figure 6 shows the input characteristics of BJT. A curve is then drawn between output current presents IC and the output voltage VCB at constant input current IE 1 milliampere. The region is known as the active region of a transistor. At saturation region, both emitter base junction JE and the collector base junction presents JC are forward biased. From the above graph, we can see that a sudden increase in the collector current when the output voltage VCB makes the collector base junction JC forward biased. Due to the forward bias, the bias emitter junction JE acts as a forward bias diode, and due to the reverse bias, the collector base junction present JC act as a reverse bias diode. Therefore, the width of the depletion region at the base emitter junction JE is very small, whereas the width of the depletion region at the collector base junction JCE is very large. The output voltage VCB applied to the collector, the base junction present JC is further increased. The depletion region width further increases. The base region is lightly doped as compared to the collector region. So, the depletion region penetrate more into the base region and less into the collector region. As the result, the width of the base region is decreases. The dependency of the base width on the output voltage VCB is known as a early effect. The output voltage VCB applied to the collector base junction JC is highly increased. The base width may be reduced to 0 and cause a voltage breakdown in the transistor. The phenomena is known as a punch through effect. Now, we are discuss about some important thing regarding CB configuration, means total transistor configuration. Now, we are talking about dynamic input resistance presents Ri. The dynamic input resistance is defined as the ratio of change in input voltage or emitter voltage, which is presents by VBE to the corresponding change input current or emitter current presents by IE with the output voltage or collector voltage VCB kept as a constant. Now, Ri dynamic input resistance equal to emitter voltage divided by emitter current. Then in this condition VCB is constant. The input resistance of common base configuration is very low. Current gain presents as a alpha. The current gain of transistor is present CB. The configuration defined as the ratio of output current or collector current presents IC or the input current or emitter current presents IE. The current gain of transistor in CB configuration is less than unity. The typical current gain of common base amplifier is the current gain is a transistor in CB configuration is less than unity. The typical current gain of a common base amplifier is 0.98. Now, alpha, alpha is present the current gain equal to collector current I c divided by the ammeter current I e. The next example is an NPN transistor has DC current gain presents by beta value of 200. Calculate the base current of IB required to switch a resistive load of 4 milliampere. The solution is the beta value is 200 and the IC is 4 milliampere. Now, IB is equals to IC by IB and the IB equal to 4 into 10 to the power minus 3 divided by 200. Now, we have the result is 20 microampere. In a common base, the next example is the common base configuration, the common base connection I e equal to 1 milliampere and the I c equal to 0.95 milliampere. Calculate the value of, now we know the I e equals to I b plus I c. Now, the second is I equal to I b the value plus 0.95 which is given in the example, the value of I c. Now, I b equals to 1 minus 0.95. So, the result is 0.5 milliampere. Now, the next example is the common base connection current amplifier factor is 0.9. If the ammeter current is 1 milliampere, determine the value of the base current. Hence, alpha is equals to 0.9, I e is equals to 1 milliampere. Now, alpha is equals to I c divided by I e and we know the I c is equals to alpha I e equal to 0.9 into 1. So, the result is 0.9 milliampere. Now, also I e equal to I b plus I c, we know the base current equal to I b is equals to I b minus I c. So, we can say 1 minus 0.9 is equals to 0.1 milliampere. In the common base connection, alpha is equals to 0.95. The voltage drop across 2 resistance and which is connected into the collector in 2 volt. Find the base current. Solution is that the voltage, now you can see the figure, the voltage drop SSRC is equals to 2 volt. We know IC is equals to 2 volt and 1 milliampere. Now, we know the alpha is equals to IC divided by IE and the IE equals to IC divided by alpha. So, the result is 1 upon 0.05 equal to 0.5 milliampere. Using the relation IE equal to IB plus IC. Now, IB equal to IE minus IC. So, IE is 0.5 minus IC value is 1. So, the result is 0.05 milliampere. For the common base circuit shown in the figure 3, determine IC and the VCB. Assume the transistor to be the silicon. The transistor of the silicon VBE is equals to 0.7 volt. Now, we are applying the Kirchhoff voltage law to the ammeter side loop. Now, we get VEE is equals to IE RE plus VBE. Now, we know the IE is equals to VBE minus VEE minus VBE divided by RG. Now, we are applying the values. The values is 8 volt minus 0.7 V volt divided by 1.5. Now we got the result is 4.87 milliampere, and also we know I c is equals to I e. So, the I c and I e value is the 4.87 milliampere. Now, applying the one more Kirchhoff law to collector side loop, we have V c c is equals to I c R c plus V c b. Now, and we know the V c b is equals to V c c minus I c R c. Now we use the values of V c c is 18 volt and I c R c value is 4.87 milliampere into 12. So, now we have the result is 12.16 volt. Now, we discussed about the applications of common base configuration. The common base configuration is a transistor amplifier configuration widely used in the electronic circuits for specific application. Its primarily advantage lies in its ability to provide high voltage gain with low current gain. This makes it suitable for application where voltage amplification is crucial, such as RF denoted by radio frequency amplification, impedance matching and signal inversion. Additionally, the common base configuration is low input impedance, making it suitable for interfacing low impedance source like antennas. It is unique characteristics also we find used in frequency mixer and signal modulator, contributing to its significance in various communication systems, especially in radio and wireless technologies. Now, we discuss more example, more common application of common base ammeter. The first is audio amplifier. The common ammeter amplifier are frequently employed in audio amplification system, such as in amplifiers for headphone, speakers and microphones. Now, the second application is amplitude modulation, denote is a AM transistors. They are used in the power amplification stages of AM ratio transistor to module at carriers signal with the audio signal. Now, the next application of common base ammeter is switching circuits. Common ammeter configuration can be adopted for switching applications such as in digital logic gates and pulse shaping circuits. Now, the next application of common base configuration is low frequency amplification. Common ammeter amplification are suitable for amplifying low frequency signals in a variety of application include audio and instruments. This example are versatile and widely used as a common base and common ammeter transistor. Amplifier configuration is various electronics and communication system. In this section we discuss in detail study of common base ammeter, common base transistor and its examples, more numericals and the application of common base ammeter, and also we discuss in this slide the input characteristics of common base transistor and the output characteristics of common base transistor. Now, in the next session we discuss about common collector configuration, and in the next slide we discuss the application of CC configuration, means common collector configuration, and the input output characteristics of common CC configuration, and we in the next slide we discuss about the input and output characteristics of CC configuration. Thank you.